Okay, so we're going to continue normal distributions. So we had an intro where we told you, hey, here's the PDF, the expected value, the variance. Here's how to calculate probabilities or approximate them using the empirical rule. Now we're going to go ahead and follow up with situations where maybe we're dealing with values that are not an exact number of standard deviations from the mean. So we're going to calculate those probabilities. And we're also going to be looking at finding the values associated with certain percentiles. So to start, we're going to have this example that we work through. So we have a character, Ginny. They go ahead, they apply to 2 colleges. Apparently, it's totally normal at this reality that the applicants all have their IQ scores submitted. I don't know. I've never applied to a college that asked me for my IQ. I don't know what it is. So they go ahead and they want to compare how Ginny does relative to the other students at both colleges. We are assuming here that the IQs of applicants to both colleges are normally distributed. However, they're not the same distributions. So they have, different averages, maybe different spreads. So given that they do have these different centers and spreads, how can we compare them, right? I mean, they have, we're going to focus on Ginny has an IQ of 120. We want to figure out how do we compare how Ginny did at college 1 to how they did at college 2 when we don't have the same distribution for both of them. So we're going to relate both colleges to our reference distribution. We have a favorite one. If we have a favorite family distributions, it's probably the normal distributions. But if we have a favorite normal distribution, it's the standard normal. So when we standardize, we have a z-score or a z-statistic where you take the x value that you're interested in. That'll be our 120. You subtract the average from whichever college, and you divide by the standard deviation. So this way it kind of takes out any units, and it just strictly becomes, well, how many standard deviations is she above the mean at each school? So we're going to suppose that their IQ is 120. So we're going to calculate the z-score corresponding to their IQ for each college. So we want to know which college they are smarter, and I'm doing air quotes, in relation to the other applicants. So we want to know which college would they be in the higher percentile for IQ. So right here, they gave us this information here. So college 1, the average is 114, and the standard deviation is 12. So looking here, this is where they're at. College 2, the average is 117, and they do have a slightly smaller standard deviation of 10. So, oops, my notifications must be on loud on my phone. Sorry about that. So we have this question now, at both schools, they did above average. But at which school did they do more above average than the others? So college 1. And I'm going to label them Z1 and Z2 because there's more than one Z-score. So it's going to be X minus mu of X over sigma. So X being just the IQ. Of applicant. So that's just going to be 120 minus 114 is the average at college 1, divided by 12 is the standard deviation at college 1. So I'm going to get 6 over 12 is going to be 0.5. So my z-score here, and it's positive 0.5. So it being positive means they did above average, and it being 0.5 means at college 1 they were half of one standard deviation above the mean. That's how they did. So college 2, we're going to do the same setup. So I'm just going to call it Z2 here because it's the second one. So x minus mu of x over sigma. So their IQ is still 120, but now we're focusing on college 2, so the average at college 2 is 117 divided by 10. So we'll get 3/10 or 0.3. So positive 0.3 means at college 2, they were above average. They were 0.3 standard deviations above the average. So if you have to think about, like, as far as if you converted it into percentiles, having a z-score of 0.5 will have more area below it than having a z-score of 0.3. So at college 1, they're in a higher percentile IQ-wise as far as the applicants and their IQs. Once again, I've never heard of any program that requires people to submit their IQs or even know them, so this is a very, very hypothetical scenario. So we're going to talk a tiny bit about what standardizing even means. So here we're going to say, okay, well, X, it follows a normal distribution with a mean mu and standard deviation sigma. When you transform it, just if I had X minus mu, this is now normal, and I've shifted it. It's centered at 0 now, and I haven't changed the spread at all. I just shifted it up, or it totally depends on what mu is. So I just shifted it to 0, so it's centered at 0. Then when you divide by sigma, now this means, oh, well, you're 1 standard deviation above the mean. You're 2 standard deviations above. So you've now translated into number of standard deviations away from the mean. So z is going to be normal 0, 1. And this one, this standard normal distribution, it's the one associated with z-tables. It's our absolute favorite. It is the favorite. Out of all the normal distributions, we love it the most. We have a table for it. It gets a special place at the dinner table, you know, all of that fun jazz. So it's a special case of the normal distribution. What the z-table is somebody went ahead and integrated it for us and put all of them into a table, which, as you can imagine, would be very, very tedious. And this table was designed to basically help us avoid needing to integrate the normal distribution. It was very, very useful. Then computing and calculators came along, and we were able to actually, you know, do the integration pretty quickly through computing. So definitely the z-table is extremely useful if you need to find probabilities by hand, but if you have access to like R, you wouldn't necessarily need it. And it's used all the time as a reference distribution. One really common thing I did back when I took AP Stats way back in the day, we wanted to compare our math scores on the ACT and the SAT. And once again, that totally assumes that you took both those tests, but they are on totally different scales. And the idea is if you standardize both of them using that z equals x minus mu over sigma, you would be able to find what percentile you were in both and compare them directly that way. So having that reference distribution, super useful. It allows you to kind of take the units and whatever out of it and compare things more directly. So still looking at Ginny and their IQ, we want to find the percent of applicants who have IQs less than them. So we are hinting at the idea of percentiles. So what we want to do is we wanted to know this blue area. This is college 1. And we went ahead and standardized and found that they had a z-score of positive 0.5. So I'm going to introduce, this is a z-table. Strongly recommend looking through. There's your turn. There are slides with videos showing like how to use a z-table. Absolutely very useful. So a z-table provides values from the CDF and specifically CDF, so probability that x is less than or equal to whatever value for the normal distribution. So here, what we're going to do, probability that x is less than 120 at college 1. I'm going to specify that because they have different averages and different spreads. That's equal to the probability that z-score we found for it is less than 0.5. Things you might notice, so with z-scores, we almost always round them to 2 places past the decimal because the z-table uses 2 places past the decimal. So I'm going to use 0.50. And what we essentially do is we separate the hundredths place from everything in front of it. So I can break this up into 0.5 and 0.00. If I combine them together, I would get back to 0.50. So I'm going to look here for the hundredths place. Oh, okay, well, I'm using 0. And look here, and this is a completely very edited table for 0.5. So 0.5. So where it lands here, that probability is 0.6915. So what this is saying is at college 1, Ginny has a higher IQ than about 69.15% of the applicants. You could also even think of this, and we'll get into percentiles, 69th or 69.15th percentile. Some people prefer to think of percentiles strictly as whole numbers. We're not too picky, but yeah. So the idea is about 69% of the applicants at college 1 have a lower IQ than Ginny does. So now if I want the percent of applicants who have an IQ higher than Ginny. So before I wanted this area, but now I want the area higher than. And I'm a huge fan of actually shading in the areas I want because you'll notice in these particular tables, they always give us area to the left. It's the blue shaded area that the tables give us. So if I want the probability that it's so if I want to know the probability of finding a student with an IQ higher than Ginny at college 1, I can subtract the probability that it's less than or equal to 0.5. So we calculate this already because remember in continuous, we can say, hey, probability that z is less than 0.5 is equal to probability z is less than or equal to 0.5. This is true in continuous random variables. Not true in discrete, so be careful. So I'm going to just say 1 minus that value from the last one, so 0.6915, 0.3085, I believe. So if 69.15% of students or applicants applying to college 1 have lower IQs than Ginny, that implies that 30.85% are above. Because remember, with any continuous random variable, the probability of being exactly 120 is equal to 0. Because if you integrate from 120 to 120, it has no width. So some probability for normal. So if you wanted to set it up here, you wanted to find a probability that z is less than some actual value. So z is just a value. That will just be your CDF evaluated at that value. So absolutely you could standardize. If you said, hey, I want the probability that x is less than a, that's equal to the probability that z is less than a minus mu over sigma. That's the idea. If you want the area above, you subtract the CDF from 1. If you want area between, you're going to take the CDF of the higher value minus the CDF of the lower value. And what you get when you take that difference is going to be just the area in between. Caution, if you subtract out of order, you'll get a negative number. It's really, really easy fix. Just reverse the order and you'll get the positive version. Okay, so we're going to look at this bridge example. There's still an average of 58 miles per hour, standard deviation of 10. So we're going to suppose we randomly select a vehicle and it happens to be going 40 miles per hour. We want to know how many standard deviations from the mean is 40. So just a glance here, 58, 48, 38, I'm going to write miles per hour. So it looks like 40, it's more than one standard deviation away, but not quite two. So it's going to be somewhere between 1 and 2. Or not just between 1 and 2, but it's less than the average, so it should be between -1 and -2. So if I want to know how many standard deviations away from the mean it is, it's essentially asking for the z-score. So I'm going to say, oh, well, z, that's equal to x minus mu over sigma. So 40 miles per hour is the value I'm interested in. That's my value for x. So 40 minus 58. So this is what I was kind of hinting at. Oh, it's going to be a negative value. If the value is less than the mean, you're going to have a negative z-score. So divided by 10. So negative 18 divided by 10 is negative 1.8. That's what it comes out to. So that means that I'm 1.8 standard deviations to the left of the mean, or less than the mean. So from there, I might want to answer a few questions. I have the z-score. I can use it to find probability values using the z-table. So the first question I'm going to ask, hey, what's the probability that I go ahead and I randomly select another car and it's going slower than 40 miles per hour? So I want this area here. So probability that x is less than 40 is going to be the same as probability that this z that we just calculated is less than that negative 1.8. I'm going to throw the 0 in there as well. So I included the z-table on the next slide. As you can imagine, it kind of gets a little cramped to put it on every slide here. So I want probability z is less than negative 1.80. So I'm going to pretend this is negative 1.80 here. And I do happen to want this shaded probability. And I can split this into negative 1.8 and 0.00. If you imagine they're the same sign and you combine them, you'll get back to negative 1.80. So 0, negative 1.8. So the probability that I randomly select a car and it's going less than 40 miles per hour, that happens about 0.0359 or about 3.59% of the time. So 0.0359. And then if I want to know more than 40 miles per hour, that's just going to be equal to 1 minus the probability that x is less than or equal to 40. So 1 minus the 0.0359. So if this is 0.0359 on the side, this white area is going to be 1 minus 0.0359. Because remember, if you add all the area under the curve, it has to add to 1. That's why I'm doing this 1 minus bit. So I'm going to get something like 0.9641. So if 3.5% of the cars are going slower than 40 miles per hour exactly, then we have about 96.41% are going faster than 40%. And that's what we're at here. So then we'll have one more part. So, well, before percentiles. So what is the probability of selecting a vehicle going between 40 and 65? So 58, 68, 48, 38. So 40 is here, and 65 is here, and I want to know this area. So first, what we're going to do is we're going to find the area less than 0.68, or not, sorry, less than 68, and then subtract the area less than 40. And it'll just give us the area we want here. So probability x is between them. It's just going to be probability x is less than 65 minus the probability x is less than 40. We know this amount already, so that's useful. But we need to take a little side quest here. Get the p-value, get the z-statistic and get the probability for this part here. So probability that x is less than 65 is the probability that z is less than 65 minus 58 over 10, or 7 over 10.7. And I'm going to add a 0 there. So if this was positive 0.70, I want to know this shaded blue area, or green. I'm not really sure what color that is. So I can break that up into 0.7 and 0.00. If I combine them again, I get back to my original number. That's the idea. So I'm going to get 0.7580. And that's this whole area from 65 and less. So remember, I still want to cut off that tail. So side quest completed. We're going to say, okay, well, this is equal to 0.7580 minus the probability that x is less than 40, which we found on the 2 slides ago, I believe. So that 0.0359, I believe. So then do a tiny bit of math here. Once again, I can go ahead, I can make things add to 1, okay. Subtraction can be a little iffy here. So it looks like about 72.21% of the time that you randomly select a car from this distribution of cars or vehicle, about that percent of the time, it's going to be going between 40 and 65 miles per hour. So over 70% of the time, it's going between 40 and 65, which I don't know if is reasonable for a bridge, but there you go. So I did hint at percentiles for Ginny and their IQ. So this is going to be similar to before, where we want to find the value. So like maybe we want to find the speed of a car that's at whatever percentile. So what you do is you find the z-score associated with that percentile. So and we'll go ahead and we'll practice. It involves working backwards. So we'll find the z-score not by calculating it, but by using the table and working outward. And then z times sigma plus mu. And that will give me the value of x that's associated with that percentile. So we talked about percentiles a little bit before. It's the value of x that has whatever percent below it, specifically below. So here we are looking at the bridge still and vehicles going on that bridge, and we want to know what speed represents the 10th percentile. So one way to think about this, if a vehicle is in the 10th percentile, that means that 0.10, I'm going to even throw in a couple zeros, is below this value. And about 0.900. We're not too worried there about that area here. So what I'm going to do, your first focus is I'm going to look at the values inside. I'm going to find as close to 0.10 as I can get, and once I get there, I'm going to work outwards and find my z statistic. So looking in here, and you'll notice this is cooked up. I totally cut this this table so it'd be convenient. Like 0.0778, no, it's too small. 0.08, still too small. 0.10. Okay, so you might notice it's 0.10 is between these two. As long as you pick one of those two, we're not too picky here. I'm going to argue that this one is closer to 0.10 than this one. So once I pick it, I'm going to pick the 0.10. I'm going to work outward. So my z statistic is negative 1.2, and then this is my hundredths place, 8. So now I have my z-score. So I did get my z-score, but not in the traditional way we did before. If you are doing a percentile problem, you will have to look here first for the value closest to the one you want, find it, and then work out. So I have my z-score. X is my unknown. Mu, we do know that's that 58 miles per hour. And then sigma is 10 miles per hour. So if I want to find the value of X, so I want to know what speed has only 10% of cars going slower than it on this bridge, it's going to be Z times sigma plus mu. So negative 1.28 times 10 plus 58. So I'm going to get something like 58 minus 12.8. It's going to be lower than 58 because it's, well, it's under the average there. Let's see. About 45.2 miles per hour. So remember, I'm still doing in speeds, so my units still are miles per hour. So what this is saying is a vehicle going 45.2 miles per hour has only 10% of cars going slower than it on that bridge. So that's what we're looking at. So it's in the 10th percentile. We have a couple more. So what speed do only 10% of vehicles exceed? So this sounds, so be cautious about the wording. It sounds a tiny bit tricky. Like, oh, I hear 10%. It's easy to think 10th percentile. But what it's saying is 10% exceed it. So I actually want the 90th percentile. You want the 90th percentile because if you have 90% below, only 10% above it. So I'm going to look for in here, in those probabilities, for 0.9000, as close as I can get to it, and then work out from there. Because my first step is going to be to find z. So looking here, 89, it's getting closer. Looks like it's between these two. So once again, honestly, you could pick either one. I wouldn't be too unhappy with either. I'm going to argue, though, that 0.8997 is closer to 0.9 than the other. So now that I have that, I'm going to work out. So I end up getting positive 1.28. Hopefully this looks familiar. Negative 0.128. So this is because the normal distribution is perfectly symmetric. If you know the 10th percentile, take the positive version of it and you have the 90th percentile. Really, really neat trick you can use. But if you can't, absolutely here are the steps you need to do to work through it step by step. So now I want to know, okay, well, x is equal to z times sigma plus mu. So I'm just going to plug in. So now it's positive 1.28 times 10 plus 58. It's going to be 12.8 plus 58. This is more doable. I believe it's what, 70.8 miles per hour. So what this means is a vehicle going 70.8 miles per hour on this bridge, only 10% of cars are going faster than that speed. It also implies 90% of cars are going slower than it. So that would be. So be very careful when you're thinking percentiles, but you see exceed, it might be implying not the 10th percentile, but the 90th. So be cautious. We definitely will word things that way sometimes. And it's okay if you need to clarify, like, hey, are you asking for higher than here? Because sometimes the way we word it can be confusing. So definitely shoot an email if you're concerned, like, hey, is this asking for higher than? We can definitely answer clarifying questions. So last one, what is the median speed? So this one, in the normal, it's perfectly symmetric. So the mean and the median are equal. So the median would be that 58 miles per hour. But I'll show you how we would figure it out from here. So I want, if it's a median, I want the 50th percentile. So I want 50% below. Well, if I'm looking here, there it is, exactly. It's, my z-score is 0.00, so I'm just going to say 0. Then I want to plug in, so x is equal to z times sigma plus mu. Well, guess what? That's just going to be a 0. So 0 times 10 plus 58. You're just going to get 58 miles per hour. So in general, something that's really, really great about the normal is how perfectly symmetric it is. You can use that information to say, hey, the mean and the median are equal to each other. And it's super handy. So you could have jumped and just said, hey, look, mean and median are equal on the normal, and said 58. Or you could have said, you know, I'm going to find the 50th percentile, find that z-score, and work backwards. Both should get you to the same answer, and I believe that is going to be it for us. Definitely check out the Your Turn examples and the R code. Super useful. There's a breakdown of like, hey, what do you put in each function? What is it doing? Strongly recommend. Take a look at it. Very useful. And we'll see you all for next week.